Hello, calculus fans! One of the main uses of the ordinary derivative in Calculus 1 is for finding maximum and minimum values. Sometimes we say extreme values. Now, with functions of more than one variable, we're going to use partial derivatives to find local maxima and local minima of functions of two variables. Let's say you're climbing a mountain, and you're trying to get to the very highest point. You might think you've reached the top of the mountain, but then it turns out you're actually at the top of a little hill. And the real mountain, the real top of the mountain, is far away and a lot higher. You've reached a local maximum. Just in your small area, it's the highest point, but there is a yet higher point farther away. You're not at an absolute maximum. So let's make a definition to say that a function of two variables has a local maximum at some point AB if f of xy is smaller than f of AB whenever xy is near AB. To be more precise, this means that f of xy is less than or equal to f of AB for all points xy in some disk with center AB. The number f of AB is called a local maximum value. And then we can do the same thing for local minimum and local minimum values. The inequalities will just go the other way. If the inequalities in this definition hold for every value of xy in the domain of f, then we're going to say that f has an absolute maximum or an absolute minimum if the inequalities are going the other direction. Now here's a theorem that we actually mentioned in Calculus 1 in passing. It's called Fermat's theorem. This one is for functions of two variables. If you have a local maximum or minimum value at AB and the first order partial derivatives exist, then those derivatives must be zero, both partial derivatives. Now the important thing about this theorem is it gives us a way to find candidates for local extrema. If both of the partial derivatives are zero, or they happen to not exist, then those are places that we should check for local extrema. These points are called critical points. The same kind of critical points that we ran into in Calculus 1. Now, not all critical points give rise to local extrema, and we saw that in Calculus 1. Your favorite example in Calculus 1 to illustrate this point is the function y equals x cubed. It has a critical number at x equals 0, but it's neither a local minimum nor a local maximum. All right, let's do an example. Let's find the critical numbers of f of xy equals 5 plus 4x minus 2x squared plus 3y minus y squared. First thing we need are the partial derivatives. F sub x is 4 minus 4x. F sub y is 3 minus 2y. If we set those equal to 0, we'll get 4 minus 4x equals 0 and 3 minus 2y equals 0. So that gives us x equals 1 and y equals 3 halves. So we can say that our only critical point is 1, 3 halves. Now if you were to look at a graph of this thing, it's an elliptic paraboloid and it opens down. So it has an absolute maximum. Now not all graphs have extreme values. If you'll remember, we talked about the hyperbolic paraboloid. It's kind of a saddle shape, and so it has no peak and no valley. We're going to be talking about saddle points as we move along here. Okay, that's all for now.